Welcome back to Physics 142. In this video, I want to think a little bit more about magnetic forces, and specifically, I want to think about how magnetic force might relate to currents and currents that are moving in a magnetic field. So far we've written down that magnetic forces depend on amount of charge times the speed that the charges are going crossed with the magnetic field, right? So this said that if you have particles moving perpendicular to a magnetic field, then you get a magnetic force. But the thing that I want to think about here is, well, moving charges make us think a lot about the idea of current, right? And so specifically, if we think about this just a little bit, maybe just unit-wise for a second, all right? Speed is just, change in position divided by change in time, right? That's velocity, I guess that's the direction, right? But velocity or speed is change in position with change in time, right? And well, you could imagine that Q, right? I could also sort of think about this as, rather than distance per time, I could think about this as charge per time. And well, what is charge divided by time? Charge per time is current, right? Our definition of current, right? Current is charge per time, all right? dq dt, all right? Or delta Q over delta T. So what I can write then is that for at least to sort of just make a hand, I'm not proving this, right, but I can make sort of a hand-wavy argument here that says that another way of writing this is that Q per time, I can write that as current I, all right? And then V then must be replaced by some distance, right? Some amount of distance. And often when this formula gets written, that distance is referred to with the letter L, because we think of a length of wire that the charge is moving in, all right? So we think of some current over some length of wire, all right? So I'll write this down maybe more fully here. So in a wire containing flowing current, all right, then we say it's the amount of current times the length of wire crossed with B, and this then says that we take the orientation of the wire, and that's what we're crossing with B to get the direction, all right? So this would be the force law, all right, for a straight wire with length L and a uniform magnetic field B. Of course, we know that straight wires are not all wires, right? Not all wires just go in straight lines, right? That often wires have really complicated paths. And so if you have a really complicated path, then we need to break this length down, right? Each of these lengths could be in sort of, little different direction, right? The current sort of flowing in a different direction, right? In all of these little pieces of wire, right? So this is like the direction of the current flow in a little piece of wire, right? And so if we need to break it into a bunch of little pieces, well, that makes us think that we need some sort of integral, right? And so if you don't have a uniform field, right, if B is different over different parts of the wire, all right, or if your wire is curvy and has a complicated path, all right, then we need to take this cross product sort of separately at each spot along the wire. We need to take the cross product separately at each spot along the wire. And so to do that, that means we need to break the wire into all kinds of little pieces, right, into just lots and lots and lots of little chunks, all right, and do that cross product for each little chunk and then integrate, right? And so if you don't have, so this, this is for, maybe I should write this down here, all right? So this was for uniform B straight, yikes, move the whiteboard a little bit there. Okay, straight L, right? If those assumptions don't apply, then the more general formula is an integral, where we say force is the integral of I dl cross B, all right, where we're going to do dl cross B, all right, and then integrate all those dl cross b's, usually we think of the current as being the same in every spot along the wire, so often the current gets pulled out, and this is written as the I times the integral of dl cross b. All right? So this is sort of the more general formula for magnetic field for magnetic forces acting on a wire. All right, so let's do one example of this. All right, and then we'll do some more examples for next class. But the example that I want to do here is I want to think about, well, let's suppose that I'm wiring up a house. All right, and let's suppose that as I wire the house, I'm going to send a wire vertically up a wall, all right? So let's say I send a wire up some wall vertically, all right? And let's say that it's 2.5 meters up that wall, all right? So 2.5 meters up that wall. And then let's say that I run that wire maybe from north to south, all right? So we'll run it, let's say north is over here and south is over here in my picture, all right? So this is, you know, I guess, what am I doing here? Here I've got north, south, and this is going to be up and down, right? So this is sort of a side view on the house, right? So this is up, and then I also run it from north to south, and maybe I run it 4 meters, you know, along the ceiling or something like that, right? So north to south along the ceiling. And let's say, you know, typically wires in a house, maybe they carry typically about 2 amps of current in them. All right, 2 amps of current. And so what I'm interested in is, well, let's say Earth's magnetic field. If Earth's magnetic field, so Earth's magnetic field, let's say that's half a Gauss, all right, 1/2 a Gauss at this spot, all right? And let's say that Earth's magnetic field points at this particular location from south to north, all right? So let's say the magnetic field is going this way, all right, from south to north, all right, at this particular spot, all right? So if that's Earth's magnetic field at this spot, then I want to know what is the magnetic force on each section of this wire, right? Because I need to know, like, are these wires going to be moving around based on Earth's magnetic field when current starts flowing through them? All right, so how will I approach this problem? Well, I need to split it into 2 parts, right? Specifically, any part where the wire is straight, I can, you know, do that with one formula. So I'll need to write down this force law for this part, and I'll need to write down the force law for this part, and do those 2 calculations separately. So let's go ahead and do that. So in the 2.5 meter wire, right, in the 2.5 meter wire, we know that force on that wire, the magnetic force on that wire, is I times L cross B, right? So that means the magnitude of that force, we need the magnitude of that force. Well, what's that going to be? That's going to be the amount of current, 2 amps, right, times the length of wire, 2.5 meters, all right, times the strength of the Earth's magnetic field, so that's 0.5, and remember 1 Gauss is 10 to the minus 4 Tesla, all right, 0.5 times 10 to the minus 4 Tesla. And what's the angle between them? Well, if B is pointing from south to north, and my current is flowing, you know, let's say my current flows up here, all right, like that, right? There's my currents flowing like this in my wire, all right? Then that's going to be a 90-degree angle, so sine of 90 degrees. And so we can calculate all those together, and when we do that, I got 2.5 times 10 to the minus 4 newtons, all right? And and the direction, well, it's V cross B, or the direction of IL. Well, IL is going to be up here, right? And B is going to the north, right? So IL is up, B is to the north, and so that would mean the answer is out of the page, and in my particular compass sort of setup here, out of the page is west, right? So 2.5 times 10 to the minus 4 newtons west. That's not a lot of force, right? That's a couple of millinewtons, and so conveniently your wires are not going to just fall off your wall from Earth's magnetic field. That's good news, all right? Okay, what about the 4-meter wire? In the 4-meter wire, all right, we still have F is I, L cross B, right? And we have I is again 2 amps, L is now 4 meters, B is still 0.5 times 10 to the minus 4, but what's the angle between them? Well, now the current's running from north to south, and B is going from south to north, so that's a 180 degrees between them, right? So we'll get everything that we got before, ditto, 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 but now we're going to have sine of 180 degrees, and sine of 180 degrees, well, that's 0, all right? So that means that we actually have no force in the 4-meter wire, and so that means that the total force on all of it must just be the force that's only acting on this upward part, that 2.5 times 10 to the minus 4 newtons. So there we have just another example of using these cross products and calculating now magnetic forces acting specifically on currents.